Hello, calculus. We were going to take the night off on videos, but because several of us have busy weekends, they preferred to watch it tonight, Thursday night. So this video can be viewed after class on the 13th, which is today, Thursday, or on the weekend. So after the class on Friday, the 14th. So whatever works for you. The topic is implicit differentiation, and we will not get to this work for a little while, but some people, they needed the video now. So let me show you what we're talking about. Previously, if I was giving you an expression in X, didn't matter how long it was or unusual it was, we could find the derivative. So we just power rule or product rule or quotient rule ourselves down or chain rule ourselves down the row. So this one, not bad at all. Okay. And then we would go back and clean it up a little bit. This type of differentiation where we have y on one side by itself and all the expressions in x on the other side, it's called explicit differentiation. And that's usually the preferred kind, but sometimes we can't get our equations to easily equal y on one side and have everything in x on the other side. So let me show you an example. And it is alright, so when we're in this situation, I see a y cubed and a y squared, so I could keep those on this side and move everything over, but I can't get y by itself. So therefore, I still want to be able to find the derivative of these expressions, so I'm going to switch to what's called implicit differentiation. Alright, so what I'll do is I'll do one by example, then I'll write down the steps, and then we'll do a second one. So that's my plan. Let me set a timer. I know I'll be going into a part 2, so I'll go ahead and take care of that. Alright. So, let's say I'm going to use implicit differentiation for the example there. And the first thing you do is you differentiate from left to right. But as you do that, so we're going to, just like you read a book, we're going to differentiate from left to right. And this expression y, we have to remember that y is representing an expression in x. It's not just a y value, it's some y equals some x expression. Like it's x squared or square root of x plus, it could be this whole thing. We don't know what y equals, but we know it is an expression in x. So y is not just treat it as the derivative of y like you would treat the derivative of x, because we're viewing y as an expression with x's in it. So, even though we can't see them. So, when we get to here then, when we do the derivative of something, we don't know, raised to the 3, you heard the keyword something, we are going to use the chain rule. So, 3 runs down in front, something is raised to the 2, but then it's followed by the derivative of that something. And that is going to be expressed in this problem as dy dx. And actually, that's what we're trying to find. We're trying to find the derivative. So when we say find derivative, sometimes we say y prime, but we use the other notation when it's more meaningful, which it is in this, dy dx. You could put a y prime there as well. All right, so that's this one. So try this one. So you treat y as if it is an expression in x. So you have 2y dy dx. And then when you come here, you have minus 5. And again, because the term has a y in it, we're going to get dy dx. And 2x follows a negative 2x, which is not followed by a special, this is just the value in x. We do not need the chain rule. And then the constant on the other side zeroes out when we take the derivative of it. The next step, we take all the terms that have dy dx in them, and we pull them on one side, and all the terms without dy dx in them, and we pull them the other side. So I chose to go in this direction. So I have 3y squared dy dx, 2y dy dx, minus 5 dy dx. And now 2x will go on the other side. And now I want to find dy dx, but I notice that it is in 3 terms, so I'm going to factor it out. It will be in every term because I set it up that way. So when I pull out and factor out a dy dx from this term, I get 3y squared, 2y, and minus 5. Since we're looking for dy dx, we have it in one spot now. We just have to peel this off of it, and we do that by division. All right, so it's gone from here, and we have dy dx equals this expression, which I would write again for clarity, but I ran out of space. So your answers when you use implicit differentiation have x's and y's in them. All right, so that's the answer. Let me check it. It is correct. All right. So let's try another one after I'll erase this and write down the rules. Or maybe I'll write the rules while it's up here. So the first rule is find the derivatives from left to right. Move terms with dy dx find the derivatives from left to right, move terms with dy dx to one side, and terms without dy dx to the other side. Factor out dy dx and solve for dy dx. Sorry, I'm blocking your view. Let me move so you can get the whole beauty at once. All right, so now I'm going to take a second example and follow those steps that you observed and now have listed. So let's look at this one. All right, copy that down. You can see this would not be very convenient. It would not be very convenient or possible to get y by itself on the left. So let's go ahead and do this one implicitly. So implicit differentiation. Here we come. So the chain rule will support us. So we have 3 times something squared, and when I do that, I'm going to know that the 2 runs down in front and combines with the 3 to give me a 6 times something raised to the 1, followed by the derivative of that something. So the derivative of that is going to be 2x plus 2y, and then because the y we've learned is an expression in x, the chain rule will take place and we'll get dy dx. On the other side, we're still differentiating from left to right, and this is a product, x times y. The 100 can stay out in front and then do the product of x and y. I usually group the constant with one of my terms and call that the first and that the second, but there are other ways of handling that. They will all come out the same. So the first times the derivative of the second, the derivative of y is 1, but then we follow by the chain rule with dy dx, plus the second times the derivative of the first. Alright, perhaps a little bit of mess, a little bit of slop to clean up here on the left. So I'll grab the 6 in a minute. I'm going to multiply this times this. So 2x squared, x squared times 2x is 2x cubed. X squared times 2y dy dx is x squared 2 times 2y dy dx. Y squared times 2x is positive 2xy squared. And when I have y squared times 2y dy dx, I get 2y cubed dy dx. Let me see how much time I've got left. Alright, I took the first couple steps. I don't want to forget the 6 that was laid out here, but I'm going to shut this down and start on part 2.